So I wanted to set a couple of expectations about this. This is in the thingamajiggy, the program as an expert course. It's really more of an intermediate, but there wasn't an intermediate setting, and it's definitely not a foundations one. So expect something pitched between intermediate and advanced here. But I think you'll hopefully pick up some useful tricks along the way, things that I've learned to do. I'm also more nervous than usual about this talk because, and I put it into words with Adrian this morning, this one really matters to me, like more than a talk has in a long time. And I hope you don't think that my baby's ugly. So at least my approach is ugly. So we're going to dig into kind of really using the Scala type system for simplicity, but also for correctness. And I work in a mixed environment where we have we're very Scala based in the company, SIBO, that I work for. But we have a mix of kind of levels where we have a lot of soil scientists and weather scientists and people like that that really don't want to deal with the kind of vagaries of a lot of the functional programming stuff. They just want something that works. And I am going to have to, oh, that's better, I can see. I'm just wondering, is anybody here a flat earther? Go on, don't be shy, stick your hands up. I see at least one hand. Okay, I think this talk will convince you that the Earth is not flat, because no one in their right mind would go to these levels of complexity to perpetrate a hoax like that. So, the Earth is not flat, okay? I'm going to start with that as a preposition. But most of the ways that we look at the Earth are flat. We deal with two-dimensional data a lot. Got a couple of examples here. Bottom left is a relief-shaded topographic map from, I think, Google Maps. It simulates 3D by having the shading, and if you move around, you actually see the kind of the elevation model change a bit. In the middle is really the best way to look at the Earth, is a globe. Okay, it really represents how things are laid out. You get to see the countries without them being all squished and smushed. Of course, this isn't a globe. This is a flat picture of a globe, and you can see how much things have been squished and smushed there, right? And then in the top is what I work with a lot. This is data from a satellite called Landsat that orbits the Earth every 16 days, produces these reasonably high-resolution images, about 30 megapixels. It's looking approximately straight down. And there's a lot of approximations in this stuff, so we'll kind of get into that as we go through. Okay, so it gets a bit more complex because the Earth is not an exact sphere either. I don't know how many of you know this, but this really matters when you're doing maps of it. Okay, because of the spin, it actually has a bit of a spare tire. We can all relate to that, I think. But it's caused by the rotation of the Earth, so it's slightly wider at the equator than it is if you go around the poles. And this makes the makes the math harder to make the maps. I will talk at the end, if there's time, and hopefully there will be, about Web Mercator, which is the most common display projection or coordinate reference system used these days. It's in Google Maps and Bing and all of those. It assumes the Earth is a sphere, and that means that Finland is approximately 35 miles from where it should be, and a whole bunch of other things like that. So we tend not to use Web Mercator for like real processing work, but it is really part of what, the display stuff. So that's the, it's not exactly round either. All right, so how do we reference some location on Earth? Well, probably everybody here, if they've ever used a sat-nav or any kind of GPS, is familiar with LatLongs, okay? And this is how they work. Choose a point in the center of the Earth, okay? You have two angles. One of them is an angle from the prime meridian, which runs through London, because that's where they set it up. And the other is an angle from the equator up towards or down towards one of the poles, okay? Longitude, as it's known, which is the x that goes around the Earth from the meridian, is minus 180 to 180, and the latitude is minus 90 to 90. If you take those two angles, draw a vector, and then intersect it with the model that you have of the ellipsoid of the Earth, you get a point on the surface of the Earth, okay? That's all there is to it. It's very simple. It's actually a really good scheme. because no matter what kind of, as the models of the Earth get more complicated, you end up with geoids. So it gets even more complicated than an ellipsoid. You start building in all sorts of other complexities to it. But with a lat-long, no matter how far you draw it based on your model, it's always the same alignment, right? It's just height is the difference. So this worked great for vector data, as we call it, points, polygons, lines, stuff like that, as long as they're not too big. When you get really big, if you've been on a plane and you notice that the plane never flies in a straight line, it flies like a curve, that's because of the curvature of the Earth. Okay, that's point one in the anti-flat earther facts there. But the real problem with it is all of those things I showed you at the beginning are what we tend to deal with in computers, which is raster data, and that is two-dimensional, and it assumes things like equal area pixels. And if you look at this, you'll see that as you move latitude, which is the y dimension, okay, the longitude values, the longitude angles cover less ground as you approach the poles. Okay, so at the equator, lat and long, 1 degree, is approximately the same. But as you approach the poles, 1 degree covers a lot more, no, a lot less, I always get that mixed up, covers a lot less distance, okay? So basically, it's no good for this raster data that we have to deal with. We have to come up with some other way of getting the data out of that. And these are the two types of data that we deal with. Vector is great when you can get it, has a lot of structure, it scales very nicely. Raster data is what pretty much everything that a satellite produces will do, because that's what we have. We have image sensors, and they take pictures, and photons go into boxes, and that's what you get. Okay. So raster images tend to assume constant measurements. The reason I'm belaboring all this is that we have to deal with the fact that we're going to be dealing with something other than LatLongs, okay? And that's where all of this comes in, coordinate reference systems and projections between coordinate reference systems. So some definitions. A coordinate reference system, or a CRS, as it will be called from now on because it's a lot easier to say, is anything that takes numbers and makes a location out of them, on the Earth or on the Moon or in the galaxy, whatever it is. A projection is anything that takes one CRS and turns it into another CRS. Okay, it's a mathematical transform. The projection plus the datum, so some center point or other things, you know, the radius of the Earth, all of these things are considered the datums, define how one CRS relates to another mathematically, and we can convert between the CRSs with varying amounts of error. And the error tends to be smaller for vector data than for raster data. We have to resample rasters, and that means moving pixels around. And literally a pixel is like a bunch of ping pong balls that have been captured in a box, and now you have to redistribute the ping pong balls, and it's difficult to do that. So therefore, we resist transforming or resampling raster data more than we do transforming vector data. A few examples. I'm not going to spend a lot of time on these because I want to get to the Scala stuff, but these are sort of some of the different ways that CRSs or projections are made for the Earth. There's conical, there's the polar kind there. Conical is sort of like a hat that the Earth wears. It's very good for the US because the US is kind of wide and not too high. So albers, the conical albers one, is commonly used for the whole US. And in the top is the Transverse Mercator that pretty much everybody learns about in school. And the way Transverse Mercator works is it's like a cylinder wrapped around the Earth. There's actually two of them, one for north and one for south. And every 6 degrees, you get a new cylinder. And then you kind of unwrap the cylinder, and you unwrap the cylinder this way. And the result is something that approximates equal area for the pixels in it. Okay, now the problem is we get a bunch of these across the United States because the States is pretty large. The contiguous 48, the lower 48 have 9 zones that cover them. Alaska has, I don't know, I think it has 5 of its own. That's a little bit disingenuous. You know, Alaska's more than twice as big as Texas. They love to point that out. This makes it look like it's smaller. I think this was made by a Texan, this map. Anyway, so this is the meat of it. Why do we care about all these CRSs? Well, there are thousands of these. They're actually defined, they've been standardized now by big oil, funny enough. The European Petroleum Standards Group now has a reference repository for all of these CRSs that you have to deal with. And the real evil here is if you get the wrong CRS, a lot of the CRS coordinates overlap in mathematical space. So here's an example of a polygon drawn around a field, and if I get the CRS, the field is now in the middle of Lake Michigan, okay? It doesn't even give you an exception, it just gives you the wrong data back. This is like the worst possible outcome, and it's really common in geospatial data. People ignore the CRS or get confused about it, drop it, it gets lost somewhere along the way, and the result is you don't get bad data, you just get incorrect data returned to you. Okay, so this is obviously very bad. I had to make it really small there because it's right in the middle of the lake, and you would have just seen a whole bunch of blue otherwise. So, all right, most systems, most languages work like this. They do runtime CRS checking. So you do something like this. Here's all the different codes. 4326 is LatLongs, WGS84 LatLongs. 32615 is UTM zone 15. If you get them mixed up, you get nonsense, or you get weird things happening, the wrong data, whatever it is. So what a lot of code will do is it will have something that does ensure the same CRS, something like that will throw an exception. And you need to put this all over your code, and heaven help you if you forget, because now you're dealing with something that you don't know what. Okay, so my idea when I came into this, and actually I have a background in GIS, so coming to do this current job kind of brought me back into it, and it's really exciting to bring my two passions together now. It's one of the reasons why this is kind of important to me. But type parameters in Scala become part of the type. This is great. I don't think this will be a surprise to anyone. Set is a great example because it's invariant. And so if you have a set of int and a set of string, they're two totally different types as far as the Scala compiler is concerned. You can't change them out. You can't use them interchangeably. And with a set, you can't just make a set of any that will take a set of int, a function with a set of any that takes a set of int or a set of string. They're just not related in the Scala type system. So I thought, well, let's see. Oh, and I should say, we're going to go a little bit into Scala variants. I'm not going to cover all of Scala variants in this. There's quite a lot to learn there. What you really need to know is invariant and covariant for this talk. Invariant means that given two different types, type parameters inside of a type, they are just different types. Covariant means that if B extends A and you have, say, a list of B, that is an extension of a list of A, or a subclass of a list of A. So they're related by the type parameters. We're not going to do contravariants in this one, but there's plenty of stuff out there if you want to see more on that. Okay, so what I thought was, we can now take those CRSs that are this problem, this easy mixed up thing, and we'll make the compiler do the work for us. It's going to track the CRSs through the system so that if somebody tries to use the wrong CRS, the code won't compile anymore. And so we start as all these things, and I think this is really kind of the art of API design for me, is doing something clever. Clever's not bad by itself, but you shouldn't impress that cleverness on everybody else. You should make it so simple that everybody else uses it and they are completely unaware of how clever you've been. I know it goes against the grain. We all want to do, oh, look at this, it's so cool. But if you can make it completely invisible, it's amazing how good that makes you feel. And in particular, after a particularly long project, somebody did some work on some stuff in Brazil recently at work, and they're like, hey, the data just came out and it's in the right place and everything. And I'm like, that's pretty rare in GIS, that somebody didn't drop a CRS in there along the way. So case classes make a great place to start for APIs, I've always thought. Here's a CRS definition. For now, we're just going to look up codes from a library. And this is all based on a library that's done all this definition. It's a Java library. It has no type safety to speak of its own. So we're trying to build that in. It's called GeoTools, but it is extremely well tested, and you do not want to get into writing a whole bunch of CRSs and testing them yourself. So we have a case class. This is LatLong WGS84, also known as EPSG4326. And we decode it, and that becomes a type in our system. Some of you may be wondering why I made that a case class and not a case object at this point, right? So why did I make it a case class? Well, there's a trick you can do with the companion if you do this, and this is something I do probably too much, but it's a really neat trick. So I can now register, and the aim here is to make a type for the CRS, but to be able to pair it with an implementation, a value that I can pull out using the type at any point. So I pass around the type, EPSG4326, and when I need the definition of whatever the CRS is, I can easily just pull that out from the type. Okay? The way we can do that is an implicit companion. So here I create the case class, I define it, and then I immediately say object EPSG4326 extends CRS type of that case class type. And inside of the implementation, I'm walking over here so I can point. Oops, but don't fall off. Don't do Martin. So what we can do is we know there's going to be an apply method, right, with a case class, because that's what apply methods do. They generate, case classes do. They generate apply and unapply. We know the type signature of that, so we can harness that. So I can use the apply method to create an instance internally and do a few other things in there. So you can here see here that I've got a CRS def, which is just a val that is the call to that apply when I need it. The rest of this stuff is not that interesting, apart from the last line. It's just things like, getting the actual coordinate reference system and the ID. The last line is a nice little trick that, again, I can't believe I got away with it. By making a pointer back to yourself, the companion object is always checked for implicits when the Scala type, or when the Scala compiler needs to solve a type problem. By making this thing extend the type class and then making a pointer back to ourselves, we make it its own implicit. Okay, it will be an implicit that's always found because it's in the companion object. Does that make sense? So basically, by just saying object EPSG extends CRS type of 4326, that now becomes the implicit type class, and these two are paired in the type system. Now, the type and the definition are in harmony. So if we make a geometry type, an abstract geometry type, and within that we specify that the CRS has to be a CRS type, it has to have a context bound of CRS type, we can get that CRS, and it's like we're passing in the CRS as a constructor parameter, but we're passing it in as a type, right? Now this thing's in the type system, but we can still get to the definition whenever we want to. And here you can see a bit of code that is just looking up the math transform for another CRS that comes in, some other CRS type, and it will look up the transform and then it will return it. So to use that, let's say we have a coordinate. Let's start with the simplest thing. So a 2D coordinate has an x and a y, and it has a CRS type. So any coordinate we make now has EPSG 4326, and then in this case, a long and a lat. Something I don't think you guys really care about, but for sanity's sake, we always put x first. So it's always long lats in GIS when we work with this stuff, otherwise it gets too confusing. Within here, behind the scenes, we use JTS, which is another Java library that's very well tested and not at all type safe. It's stringly typed, in fact, a lot of it. So we want to hide that as much as possible, but it is used behind the scenes because, again, we don't want to deal with a lot of the stuff that's already been written and well tested there. But I can take a coordinate in some CRS and I can transform it to another CRS, at which point we get back a new type. Okay? Let's say I take 4326 and I want to convert it to 32615. I would say coordinate.transform CRS, EPSG 32615. That gives me back the new type, and it does the transformation behind the scenes, right? So somebody coming in, they get some CRS in some random, or some point in some random CRS. They need it in another CRS to satisfy another part of the program. In order to get that, they do the transformation, whether they want to or not, because they have to get it to compile. All right, and pretty much the rest of that is the plumbing. Everybody with me so far? There'll be time for questions at the end, but if anybody is really having like a burning question right now, you can stop me. All right. So by doing this, the compiler now has your back. We can create a coordinate in EPSG 4326. You can see it up there. That is in the type. So everything has a CRS now. This is one of the rules of GIS. Nothing gets, even in like non-typed solutions, nothing is allowed in the system without a coordinate reference system attached to it. And in our case, we don't allow anything in without a CRS type anymore. So everything we create has a CRS type and it's tracked through the system. So coordinate 2D in LatLongs, there we go. I have down here a method that requires a coordinate 2D in LatLongs 4326. I can call it with a show map, and that works. Okay, it says, oh, I'm showing the map at those coordinates. If I try and call it with a coordinate in 32610, in this case, which is the California UTM zone, it will give me a compile error at that point. Even better, IntelliJ will tell me what's wrong. And look, it's actually a readable error message as well. This is great, right? Don't underestimate the power of this. To somebody who is just a soil scientist and they're like, oh, it says it needs a coordinate in 4326 and it's got one in 32610. At least at that point, they know where to start looking. So, and of course, you can make it work by transforming it just in time to the CRS that you want. So, somebody at this point should have said, but there's a flaw, okay? All of this assumes that you know what the CRS is at compile time. And it's a harsh world out there. The Scala type system only exists in one place, and that's inside the Scala compiler, right? The rest of the world doesn't give a damn about the Scala type system. So at some point, you have to bring this thing in, and when you do, it could be from some source, and you just don't know what the CRS type is going to be. So for this, we need some kind of type. Literally, you'd say it as, I've got this coordinate for some type, for some CRS, okay? Anybody heard for some recently? I know it's going away, but you know what that is? Anyone? Yep. I didn't hear it, but I'm going to assume you were right. It's an existential type, right? It means there's some type here, but I don't really know what it is, but it is unique in the Scala type system. So we need to make an existential CRS. You're saying there's some CRS here, it's valid. I don't know what the type is, but what I want to make sure is that it is unique within the Scala type system. There's a really easy way to do this. You can make a trait. Within the trait, you can define the type, and you can define its implicit companion right there with it. You can give them the same name, and then when you import them, they come in as a pair, okay, and you can use them. Now this CRS, we don't know what it is, but we know it's valid because there's an implicit companion with it, and the only way we can create that is to actually find something that satisfies that coordinate reference system that we need. So we have some type. It's unique because it's path dependent. Okay, whatever we access this thing through when we create an instance of one of these sum CRSs, that capitals, all capitals, sum CRS there is going to be unique in the Scala type system. And I probably shouldn't do that because it looks bad on the camera, but I can't see anybody, so. So this lets us do something like this. We can go, we can write something which just looks up a CRS, whatever it is from, say, a string, an ID, and it will give us back, in this case, an option, or it will throw an exception, but it gives us back the type and the implicit that satisfies that type. So now when we come to use this, we can say, oh, I've got a point coming in. Here I've written it in a test, but it might be defined at the top of a shapefile or something like that, or in a sidecar file usually with shapefiles. And we can look that up. We can create a type for it that's unique. We can look up the details for it, and we can give all that back. Then what we can do is with that item that we give back, the sum CRS instance there, we can import .sum CRS from it. That brings in the type and its companion. That makes it a real CRS type in our system. It's now unique, okay? At this point, we need to reify with what we know. So this is where we do the transform. And if you've written the transform correctly, and it can say, oh, well, this is already one of those, then you can do a simple cast behind the scenes. You don't need to transform anything. But otherwise, you can transform it just in time to what you need. Okay? The other way of doing this is sometimes you'd never find out what the CRS is. It's still a unique type. It starts in one UTM zone, and you go quite happily through your entire program using that unique type. Okay? It doesn't matter what it is. It's still consistent. We know that everything else has to be converted to that type in order to work. So it works both ways. It's great. So when we're dealing with rasters, as I said at the beginning, we tend to resist resampling them because it's a lossy operation. So everything else that we deal with gets converted to that existential CRS instead as we go through. It gets the transformation and goes through to it. This is probably a bit small, but this is a polygon. You can see the slides afterwards. The main thing about this is it uses the coordinates, inside, and it uses the transformation on each coordinate. And then you can see that in the transform CRS there. So that takes its context bound, and these context bounds chain up, right? They're done through implicits, they automatically chain up through the system. So we know, because we've got that CRS type on there, that the coordinates can be converted, and then at the end of it, we can just give back a polygon in that new CRS. All right. The result of this is that the API is now really hard to get wrong. It's just about foolproof. It really is. About the only way you can screw it up is when you make the pairing between the CRS and the implicit companion that you type in something wrong. So don't do that. Don't do a typo there, or you'll end up pairing the wrong type with the wrong definition. But as long as you don't do that, the rest of it's pretty good. About the only other way you can go wrong is to put something in your system without a CRS type on it, and that doesn't make it past code review. So that's how we get around that. So just something I wanted to point out here is that Scala Test has a really nice feature for this, which is if you want to check that something doesn't compile, you can write a test for that. I'm not sure if you've seen that before, but you can put a string with the code in, and then you can say that should not type check. And if it does type check, it means that you've failed the test, okay? And you can see down at the bottom there, I wrote out that same thing, and you can see what it tells you is type mismatch expected coordinate in EPSD 32615. It actually got one in 32616. We now don't have data in the middle of Lake Michigan, which is good. All right, a little bit more nuance. Actually, I'm doing well on time, so this is going good. A little bit more nuance. At the beginning, I showed you the angles, the angle types, LatLongs, and the UTM zones are meter-based. Okay, everything you give, the X and the Y, are approximately meters, and there's actually a guarantee of how accurate they are. There are maths people that love this stuff, man. Everything's defined. The accuracy of the thing, how much the pixels can drift in terms of their size from one place to another. One thing you learn very quickly is that all spatial data is an approximation, but you're trying to keep that approximation as close as possible and minimize the errors. So within a UTM zone, I think it's like something like 0.1 of a millimeter for every meter is the maximum drift that you can get, or is it? No, it's more than that. It's like 1 millimeter per kilometer. It's a tiny, tiny error in there. So one of the other things, if you think of the LatLongs, and you remember how I said that as you go up in latitude, the longitude values change, the amount of area you cover on the ground based on the angle changes, that affects the area. An area on an angle-based CRS is really weird because you can take the same field and move it to a different latitude and get a totally different number for the area, right? Or, you know, at least the area on the ground. So it's kind of weird to ask for an area like that. And so what we can do instead is introduce some new abstract classes in there, and we can say, oh, I nearly did a Martin again. It's easy to do, anybody who's wondering. So we can say there's an angle CRS type and a meter CRS type, and they are both CRS types. And then when we define these things, we would say 4326 is an angle type, 32610 is a meter type. And if we do that, we can say things like this: area in square meters, and we will only accept CRSs now that are meter-based, okay? And it won't compile if you use something else. It will tell you what it says down the bottom there. Could not find evidence that EPSG 4326 is meter-based, is effectively what that's saying. So you can take it further. You can introduce a lot of these kind of nuances. Another thing you could do here, although we resist it, that's a whole other conversation, but you could introduce squance units here, right? You could actually say this is the unit for this thing. Okay, so that's CRSs. That's about as far as I'm going to go, but it really does work, this thing. Like I said, I think during the beginning there was a bit of grumbling because there was all of these compile errors that people didn't used to see. And after a while, you know, I would point out to people, well, this was a bug, and you would have got the wrong data back. And nobody complains about it anymore. It's actually worked out really well. People seem to like this. So let's switch tracks. Another place where we don't have enough type safety. In GIS, we deal with things called features a lot. Features are things like fields and counties and maybe a country boundary. Maybe it's a point of interest. Maybe it's the nearest McDonald's point of interest on your GPS, whatever. That's a feature. And it's a geometry with attributes on it. And the attributes, long story, a lot of history here. For the most part, the accepted types for those are whatever fits into a Visual Fox Pro or an old Fox Pro database. That's just because that's what shapefiles were based on in the first place, and then that grew into pretty much everything else. But within the API, within the Java GeoTools API, those attributes end up being a map of string to any, and that's where you play the sad trombone, because that's where things go horribly wrong when you see a type signature like that. And it leads to all sorts of abuses. We've just hit several in the past few weeks where people get the attributes and they're like, save it out to a shapefile. And you know, it hits and it's a map of string to any. Nobody's broken any rules up until that point, and it's like, I don't know how to save a, 365-day weather array into a shapefile. So this leads to all sorts of abuses, and we can do a lot better. We can, of course, make it completely type safe, and we could do a lot of things with type classes and stuff like that, but it's nice to have this, as I'm going through processing, the ability to just kind of lop attributes in there still and retain the type information. And for this, many, many years ago, a good friend of mine called Chris Voigt showed me, actually, this is the feature definition. Let's go through this first. Very quickly, it has a CRS. Everything has a CRS. The attributes at the end there, the T, is covariant. It's a covariant type parameter. And we have a method in there that allows us to take a function from T to U, and it will give back a new feature with the transformed attributes, but everything else the same. Okay, that's just a little bit of mechanism there. So, simple covariant behavior. We can look at this. Because list is also covariant, we could make a function that takes a feature that requires a list of any, and now we can call that with any feature that has a list of some kind as its attributes, and it'll work. So in this case, it's just returning the size. So it works for a list of int, it works for a list of string. It doesn't work if we pass it an int. That's a compile error, because that's not a subtype of list there. This is what I was telling you my friend Chris showed me many years ago, and I've come back to them just occasionally. And it's a very few lines of code, and some of them aren't even necessary for it here. They're conveniences. This is a type indexed map. And you can sort of think of it as approximately what an HList is to a list. This is to a map, okay? The difference here is that the keys in the map are types, and they're type tagged. Type tags are not a part of this, although I'm happy to go into them another time when there's more time, but they are effectively a conversation between the compiler and the runtime. It's a bundle of stuff that the compiler knows about the type that you're talking about, shoved into the runtime so that you can examine it, okay? And we can use this as the key to our map, and we can do some behind the scenes, some casting. Now everybody's like, oh, casting. Let me tell you, the Scala type system doesn't exist in the real world. It only exists in the Scala compiler. Any time you get a type from no type, there has to be a cast somewhere. It doesn't matter how well it's hidden. Something somewhere is doing a typecast. So we do this here. Okay, and what we do is, there's a bunch of type safety here, but I'll show you how it works in a minute and it'll make more sense. The main thing that I want you to see is that when you create something, you pass in a value with some type, with some attribute type. It implicitly passes in the type tag. It uses that type tag to store the type in there, and you can pull it out by that type again. So you can do a get square brackets e, and what's I think more interesting is, at least for the, actually not the get but the apply, is that we use lower bounds here. E, the type coming in, must be a super type of T. Okay, we use that to make sure that it won't compile if you try and ask for a type that isn't in the T map. This will make more sense when I show you how it runs. So here's an example of it, and hopefully this will now make sense. Particularly look at the middle one. We start with a T map that is just a T map of int, okay? And then we can add a string to it. We just do tmap1 plus hello. The type at that point is now intersected. And actually one of the things I'm going to do when I have time, and that will be very soon now, is take this and put it in .e and see how things change and how things work. I'll talk about that if there's time in a minute. But when we add the string to it, the tmap, the type that we get back is now a new tmap, and the type is now an int with a string. Okay? If we add a list of things to it, a list of ints to it, we now end up with a tmap of int with string with list of int. Okay? And we can see down the bottom here, actually there's a method missing here. Tmap. Oh no, that's okay. That's just showing you access. Okay. Here's what we care about. Let's say we have some calc method and it needs the list of int and the int attributes from that tmap, but doesn't care what else is in there, okay? Because it's covariant, something with a string, an int, and a list of int is a subtype of that. So we can pass it in, and it will use just the things it needs. It will grab them. So you can see here, tmap3, which is our int with string with list of int, that works when we try and call calc. But passing tmap2 in, which is an int with a string, doesn't match the type signature, and the compiler tells us that that's no good. This can be extended, of course. I don't think it's much of a stretch to take it to serialization, for example, where we want to write something out to a shapefile. We now have to show, we still have all the type information, and we now need to show that we can turn whatever this thing is into a type signature, into a shapefile attribute, and so on. Here it is with attributes. The feature now, and I think this is where it gets to be quite interesting. There's a lot of type stuff going on in this one. Features we don't want to limit to just being tmaps. That would be silly. We could put rich types. We can, and many times we do. Tmaps are a kind of a, they're not to be overused. They're convenient, but a lot of the time, if you can get away with a case class that represents all of your attributes, do that. That's a much stronger, more readable way of doing things. But if we're just lopping things in there, kind of throwing things in a bucket, maybe we have something like this. So the feature now takes some type T, and then you can see down here there's a private def add attribute inner, and that says if the TM, if the TM here is, and this is a new type, is a subtype of TMT, as type map of the inner type of that thing, whatever that is, and I've got evidence that T is a subtype, yes, of the TM. Is that right? Yes, T is the subtype of that TM. Then we can call this operation. And what this means, this is pretty typical use of like equals colon equals or less than colon less than. It means that this method can only be called when it's a tmap in there, basically. And if it's not a tmap, it won't compile. And then down the bottom, you'll notice that's private, and down the bottom I've got a rich class around it. I'll talk about why in a second. All right, so in use. In the stuff I do, we have harvesters, high-tech harvesters that rumble around fields, and they count when they're harvesting, they count the amount of stuff coming in and how long it came in for. So it's a flow rate and a duration. If you multiply the flow rate by the duration, you get a yield for that particular period of time. You get how much stuff came through the harvester in that particular period of time. So if you take a flow and a duration, you can get a yield out of it. There's a function that does that. It takes a T-map of flow with duration, and it doesn't matter what other attributes are in there. We just need those two types in there. We give back a yield, and then down here in the code somewhere, there it is, we say, actually no, it's not that one, it's the one down here. We say feature no, right up there. Feature with flow and duration, we can add the attribute, and the attribute we're adding is the calculated yield, okay? That whole thing's type safe. You'll notice that after that, the whole feature becomes now a T-map with a field name of field name with flow with duration with yield, whereas before it was field name with flow with duration. So we are accumulating these things in a type safe way as we go through, and everything compiles when it should and does not compile when it shouldn't. If we give it field name with just yield, we can't call the calc on that. Okay? This all making sense? Or have I lost everybody at this point? Hopefully this is neat. All right. Why do we have the implicit extension class? I have 3 minutes left, so we should get through this. And there may be a better way to do this. I stopped looking after I made this work, and it occurs to me that I probably shouldn't have done that, because I bet somebody else has a really neat way of doing this. But this is my solution to this problem. First of all, because T is covariant, you can't use equals colon equals there, because both of the type parameters in equals colon equals are invariant. So that breaks the contract. Okay? The only one you can use is less than colon less than. Less than colon less than has some interaction with the Scala type inferencing that breaks it being able to inference properly here. So when you do this, if you do it using the add attribute directly in there, you'll get this error. Cannot prove, and it's not just an IntelliJ error, this is from the Scala compiler, cannot prove that T-map from escalate whatever field name is a subtype of T-map of nothing, right? And is it subtype? No, it's supertype, isn't it? It's up the hierarchy. You get the idea anyway. It infers nothing, and it can't fix that in time. So by introducing, oh, and if you use equals colon equals, as I said, those are invariant. Here's the signatures from the Scala source, from the Scala core libraries. And you can see from and to are invariant there, whereas in the case of the second one, to is covariant, so we can use T in that place. All right, so the rich feature, if I go back to that, what that does is right here, it allows us to fix the type T. So this thing's created, and when we create it, we fix the type. So there's no longer any need to infer it and get this nothing that's at the bottom of the hierarchy anymore. So at that point, it freezes that type in place, and then we can call the add attribute, and we have the original type and we have the new attribute, and we union them together. We intersect them, and that becomes the new type. All right. So the one last one I'm going to hit in the dying seconds is a couple of safety latches. Easy things to do, but inspired by SIP 18, which is the import language features. We wanted to make it so that it's not impossible to resample, but you have to really want to do it, and you're not going to do it by accident for rasters or coverages, as we call them. So you just make an object called resample CRS, and inside of that, there's another implicit class that adds the resample methods that you need. Then, in order to resample something, you have to say import resample, what did I call it? Resample CRS? Yeah, resample CRS _. And when you do that, you're then able to say .resample CRS to some new CRS, or provide it with resolution and an interpolation that you want to use to resample it. And I think at the beginning I mentioned Web Mercator. This is the definition of Web Mercator. It's under something called display only, to give the hint that you have to import display only if you want to use Web Mercator, and that's a reminder to people that this shouldn't ever be used as part of the processing pipeline. All right, so the puff pieces, the mandatory bits. If you like this idea or other stuff, or you like programming in Scala, we're hiring. There's the career, the one you want is really the one at the bottom, cebotechnologies.com/careers. And if this whetted your appetite and you want to brush up on your types, we do training, Escalate, and the training links you can find up here. There's online, and we can do in person by arrangement. So that's it. Any questions? I can't believe I timed that quite as well as I did. It's literally like 46 minutes, so I overran just by 1. But thanks, anyway.
This is excellent work. Are you planning to open source this?
Yes. Oh, good. Thank you for reminding me. It will be open sourced, I hope, by this weekend. It is based on work that I've done at CBO. So being a kind of conscientious person, I did run it through legal and the other bigwigs, and I'm certain, though, I mean, the code's up on the slides, right? What are they going to do now? But that's part one of the reason. Part two of the reason is there's some changes that I left on my laptop at home and forgot to check in before I left. So I'm going to check those in. By the weekend, should be up there open sourced.
What will it be called? How do we find it?
It will be under how do I get that out there to people? It'll be under escalatesoft.com, the organization on GitHub, and it's called Scala Types. But I don't know how to message that to people afterwards. Somebody here must know that. Okay. We'll figure out a way.
Okay.
Sorry? Scala announce list. Okay, I'll put it on the Scala announce list. That'll work. Okay.
Can you tweet out the slides too?
Oh, yep, absolutely. I think the slides come as part of the package with Scala Days anyway, but yes, I can PDF them and put them out there for sure. Okay, great. It is literally just what you see. There's not an API here, right? It may grow into one. Most of this is based on kind of cleaned up versions of internal code at the moment, so it's just enough to show the types and stuff like that, but I hope it will grow into a type-safe open source Geo API in time. Anything else?
One more.
Yeah.
Are you planning on reviving the Scala Wags podcast?
The Scala...
Scala Wags.
Oh, yeah, we get asked that question a lot. I'm not saying no, but Josh was really the anchor man. He was the driving force, and he's been super busy, and he's had lots of other really good reasons why he's not doing that. I think the next in line for being the anchor person would be me, and I've been kind of busy too, so I've been unwilling to take on the responsibility. But we're not saying no. I'd like to do it again. I miss talking with my Scalawag buddies, so maybe, but no promises. All right. One more, yeah.
So a lot of this work for using type systems to enforce business logic is really awesome, but from the soil scientist perspective, some of the type signatures can be pretty verbose. How well does the Scala type inferencer work for what you've done here?
Scala type, oh yeah, I put all of the explicit types on there to show you guys what was going on. Almost none of them were required. It will infer, you don't have to put coordinate 2D, EPSG 4326 or anything like that. It will all be inferred. It's very rare to get something in this that doesn't get inferred like that. Like I said, I mainly did it to demo it on the slides and make it explicit for you guys. And as far as the verbosity goes, people have asked this. They're like, why do I have to put one of these CRSs on everything? And my answer to that is, you would have a CRS parameter there if you didn't have the type, right? It's one of our golden rules that nothing enters this system without a CRS attached. So you're going to have the parameter in there at least. By making it a type, yeah, you pay a cost when you're defining a method that you wouldn't otherwise. You could kind of gloss over it there. But in anything that you define, it's really no extra cost. You're just moving something that was a runtime parameter into a type parameter. And it's now type safe and compiler checked, but not that much more typing. So
makes sense. Thank you.
Sure. All right, well, I think that's it. Thanks, everybody. Have a good lunch.